The moment generating function is given by mx of t, which is equal to the expected value of e to power tx. Different for it is summation for discrete random variable, while it is an integral for a continuous random variable. The cumulant generating function is kx of t, which is the natural logarithm of the MGF. The first, when it is evaluated at t is equal to 0, the first one will give you 0, which is the first moment about the mean or the central moment. The second one will give you the variance, which is the second moment about the mean. Expected value of xm can be obtained using the moment generating function. D, that is differentiating the MGF n times and evaluating at t is equal to 0, will give you the nth raw moment of any random variable. There are several properties of the moment generating function. The first property listed here is that the sum of two independent random variables, the MGF of the sum of two independent random variables is equal to the MGF of the product of the MGF of both random variables. Also, number 3 talks about the sum of two constants, the constant a plus b, another constant multiplied by the random variable x. The MGF is given by e to power at multiplied by the mx of bt. The fifth principle or property is that the sum x plus a all over b, the MGF of that is equal to EATB times mx t over b. Go to the next page. Example 1. To show that the MGF of the binomial distribution is equal to q plus PET to power n, and we use it to obtain the first two moments. Note that from the principle of the binomial distribution, p plus q always is equal to 1. P plus q is equal to 1. P is the probability of success, q is the probability of failure, and their sum always is equal to 1. Now the PMF of the binomial distribution is given by this n combination x multiplied by px times q to n minus x for values of x between 0 and n, which is the size of the sample. So, for us to obtain the MGF of the binomial distribution, we have to note first that it is a discrete probability distribution. It is discrete and it needs summation in the computation of the MGF. In that regard, MST is equal to the sum from 0 to n of e to power tx multiplied by the PMF. This is the PMF, which will give us this. The next item after the equality sign, where we are trying to rearrange the terms until we get to this n combination x multiplied by PET to power x time then by multiplied by q to power n minus x. We note that by the binomial theorem, if you have any two real numbers, p plus q, to power n, then it is just the sum of the binomial expansion. It is given by this. This component on the right hand side of this equation is the same thing as what we have earlier on here. Is a similar thing to what we have in the earlier page. So what we will have to do is to rearrange them and note that PET, where this one is now representing the new P, plus Q to power n will be the same thing as this. Will be the same thing as this. And when we have done that, it's just for us to have a look at what is on the right hand side of our earlier computation and see that this left hand side PET plus Qn is equal to that sum, the sum. That is to say, the MGF of the binomial distribution is PET plus Q to power n, which is equal to Q plus PET to power n, which is what we are expected to prove as required. So the you can also have the expected value differentiating it the first time and evaluating as t is equal to 0 to give you np as the mean. Also, when you differentiate two times, you have and evaluate at t is equal to 0, you have np into bracket 1 plus n minus 1 p, close the bracket. And with that, you were able to obtain the variance, which is expected value of x squared minus expected value of x all squared. And it will be equal to npq, which is the variance of the binomial distribution. Now, the next example is that show that the MGF of a Poisson random variable is given by MST is equal to e to power lambda into bracket et minus 1 and obtain the first two moments of the distribution. As well, we have to state the PMF first of the distribution. Take notice the discrete distribution and the from first principles the MGF is given by expected value of ETX. Using summation as a discrete distribution, we have what follows next, and thereafter we have to rearrange the terms, put those terms that have the same power x together, which is what has been done, so that we now take note that bet lambda x by x factorial, this the summation of all these things is equal to 1. The reason for that is not far-fetched. This is because it is a probability dense mass function, and as a property of that, or the sum of all possible probabilities for any probability distribution, be it discrete or continuous, is equal to 1. In the case of a continuous, instead of summation, we'll be talking of integral. So integral is also a form of summation. Let us take note of that. So you can see that when we now continue our rearrangement, you multiply the numerator and the denominator by exponent of lambda e to power t will yield for us, upon rearrangement, this can go out. The next line, we have e to power lambda et minus 1, then summation from 0 to infinity of this term, which will now give us 1 is equal to 1. So we will now have what is left again as e to power lambda into bracket et minus 1. Therefore, the MGF of the Poisson distribution is e to power lambda into bracket et minus 1. With that, you will be able to differentiate the MGF of the first and the second time to obtain the first and second moment when you evaluate it at t is equal to 0. And from there, you will also be able to obtain the variance. The first moment expected value of x is equal to lambda. The second real moment is equal to lambda squared plus lambda. And the variance of the Poisson distribution is equal to lambda as well. The mean and the variance of the Poisson distribution are the same. For the above example, the cumulant generative function, that is for the Poisson distribution, Ks of 0 is equal to 0, and K prime of 0, which is the variance, is equal to lambda as shown in the previous discussion. Example 3. Find the moment generative function of a uniform random variable on the interval a, comma b, and obtain the first two moments, expected value of x and expected value of x squared. Hence, find variance of x. The solution. We have to take note that this is a continuous probability distribution given over the interval a, closed interval a, comma b. The PDF of the uniform distribution is 1 all over b minus a, and the range of values is a less than x less than b. So the MGF from first principle is the expected value of tx. Going through this, we have to incorporate etx, then f of x, then dx, which will give us 1 over t to bracket b minus a multiplied by etb minus eta. Now, for us to that is the MGF of the uniform continuous distribution. Now, for us to obtain the first moment expected value of x, we have to differentiate the MGF once and evaluate at t is equal to 0. Going through the differentiation, we are going to use the quotient rule, which says that because you have quotient there, v du ds minus u dv ds all over v square. That is the quotient rule for differentiation of quotients. Let us take note of that. That is what was used to obtain the relationship 1 over b minus a into bracket this, and you now evaluate it at t is equal to 0. You can see there is a t equals 0 there, t at the top, and t at the one of the t can cancel out to have everything will now be b etb minus a eta minus in brackets eta minus etb. This is 0 minus 0 all over 0. So you have 0 over 0, which will make us to use the principle of L'Hopital rule, L'Hopital's rule of determining indeterminate forms. It is an indeterminate form 0 over 0. We differentiate the numerator and the denominator once and evaluate again to see whether it is still indeterminate. So when we do that, we differentiate the numerator and the denominator. It becomes 1 over b minus a et expected value of s is equal to 1 over b minus a into bracket t b square etb minus a square eta over 2t. That is what it refers to. And when you evaluate it at t is equal to 0, the t at the numerator cancels the t at the denominator, and you now have 1 over b minus a into bracket b square etb minus a square etb all over 2, which will now give us b square minus a square over 2b minus a, which upon resolution, rearrangement, and a little cancelling out, you have b plus a over 2, which is equal to a plus b over 2, equivalent to the mean of the uniform distribution in the range a and b. Similarly, we can have expected value of x squared obtained in the same process using the same process. You differentiate mxt twice and evaluate at t is equal to 0. And you use L'Hopital's rule to resolve any indeterminate form that you may encounter in the process. When we have done that as an exercise, you have to verify this yourself. You see that the variance of the uniform distribution in the interval 0, a comma b is b minus a all squared all over 12, which you can verify by yourself. Let us now go into the hypergeometric distribution. The hypergeometric distribution. It is applicable when we are sampling without replacement from a finite population, which has only two types: success or failure, black or red ball, membership of a committee or not member, male or female in a class, and any other situation where you can segment the population into two groups. Now, there are many ways that we can make use of this binomial, I beg your pardon. There are many ways that we can make use of the hypergeometric distribution, even in situations where there are more than two groups. We can say one of them is the first group and every other group is lumped up as the second group. For example, you have a class where you have 100, 200, or, and 300 level students taking the course. For example, okay, let's say, for example, STA 132. You have 100, 200, 300, and even 400 level students taking the course as a result of carryover. And you want to establish certain principles of sampling. You can say let the 100 level students be the first group and every other group comprising 200 level, 300 level, and 400 level students are taken as a second group. So you can always make use of that kind of categorization. And when you are sampling without replacement, you are able to make use of the hypergeometric distribution. P of x, or the PMF of the hypergeometric distribution, is given by k combination x multiplied by n minus k combination n minus x divided by n capital N combination small n, where x takes values between 0 and small n. X is the random variable that determines the number of successes in n trials on in a sample of size n, sampling without replacement. Let us take note of that. It is sampling from a finite population without replacement. So the n is the size of the population, capital N is the size of the population, small n is the size of the sample, k, capital K, is the number of elements of the first type in the population. So those are the parameters of the uh, hypergeometric distribution. It has a lot of applications. There is a contingency table for sampling without replacement of, for example, x red balls and n minus x blue balls. That is, you are sampling a sample of size n, x red of them, of the balls, and x minus n minus x blue. Only two set of balls are in that on. And the on ultimately contains k red balls, capital K red balls, and capital N minus k blue balls. That is the total number of balls, either red or blue, that are in the on is equal to capital N, which is the size of the population. So this is the contingency table. If you draw x red balls, then you did not draw k minus x red balls, which gives you a total of k red balls. So if you draw x red balls without replacement, there's no replacement. What is left of the red ball is k minus x. If you draw n minus x blue balls, what is left of the blue balls is you subtract this n minus x from the n minus k total. So this is n minus k minus n minus s, which we have now resolved to look like this. And you have a total of capital N minus k blue balls. So the total size of the sample is small n. The entire size of what is left in the urn is capital N minus n, and the total size of the urn is capital N. The PMF of the hypergeometric distribution can also be expressed in the form P of x is equal to n combination x multiplied by capital N minus n combination k minus x, all divided by n combination k. And the reason for this is simple. It follows from the symmetry, and in a matter of expressing the PMF by way of the actual factorials. N combination x is a factorial is equal to n factorial over n minus x factorial, then x factorial. The same thing you can express n minus n over k minus n minus n combination k minus x. You can express it as a factorial as well, and so on. That is for the PMF, the original PMF given by is k combination x multiplied by n minus k combination n minus x divided by n combination n. So when you resolve it into factorials, you rearrange, you will get this relationship given by this equation. So it can be represented by that again. Now for the hypergeometric distribution, the mean is equal to NP, where P is equal to capital K over N, the probability of success, the population probability of success, which is known for the hypergeometric distribution because we are dealing with a finite sample. Take note, what differentiates the hypergeometric distribution from the binomial distribution is that you know the actual population probability of success P, and is given. Why for the uh, binomial distribution you don't know that, and you are sampling with replacement in the case of the binomial, but you are sampling without replacement in the case of the hypergeometric. So the variance of the mean is given by NP. The expected value of x squared is also given there, as well as the variance, which when we do all the necessary rearrangements and realignments, you will find out that the variance of the hypergeometric distribution is given by npq, n into bracket n minus n all over n capital N minus 1. Now the limit of the variance of the hypergeometric distribution is when n is tending to infinity. When n is becoming too large, you can see that these two things, what is multiplying the npq, will be getting close to 1, and it will now become npq, which is the variance of the binomial distribution. Therefore, the hypergeometric distribution approaches or is a limiting form, or it approaches the binomial distribution as the population size becomes very large. So the binomial distribution is a limiting form of the hypergeometric distribution. So that will be all for the explanation from the notes that we have just projected. Thank you.